How did everything start from nothing? This question is not merely an academic pursuit. It is a profound philosophical mystery that continues to captivate our collective imagination. It's a question that touches upon the deepest aspects of existence itself, one that challenges our understanding of the universe, time, space, and the very fabric of reality. The idea of creation from nothing, ex nihilo, forces us to confront the unimaginable, a state where there was no time, no matter, and no space, yet somehow everything we know and experience came into being. This is not just a question for philosophers and theologians, it is one that scientists grapple with as well. In fact, this question cuts across the boundaries of disciplines from cosmology to quantum physics, compelling us to explore how the universe, in all its complexity and vastness, could emerge from a state of nothingness. This documentary aims to explore this mystery, guided by the combined forces of cosmology and particle physics, and to understand how science is attempting to answer a question that has confounded thinkers for centuries. The intersection of science and philosophy becomes particularly fascinating when we consider the laws of physics. Can the laws that govern the universe explain how everything came from nothing? Is it possible that the universe in its entirety came into being through some inherent quantum process, with the fabric of space-time itself being born from a vacuum, a void? These questions are far more than abstract. They are fundamental to our understanding of the universe and of ourselves. They invite us to rethink the very meaning of existence, the nature of creation, and the boundaries of what we can know. As we venture deeper into the realms of particle physics and cosmology, we are confronted with concepts that seem at first glance to defy common sense. Particle physics, the study of the most basic elements of matter, offers a glimpse into a world that operates on a scale far beyond our daily experience. Here, particles like quarks, electrons, and neutrinos are the building blocks of everything that exists. These particles are so small that they defy our conventional understanding of space and time, challenging the very laws that govern our world. Particle physics operates under the principles of quantum mechanics, a branch of science that reveals a world both mysterious and counterintuitive. In the subatomic realm, particles can be in multiple places at once. They can interact without physical contact, and they exhibit behaviors that defy the predictable nature of classical physics. At the heart of this quest lies the Standard Model, a theoretical framework that describes the fundamental forces and particles of the universe, excluding gravity. The Standard Model has been instrumental in explaining the behavior of particles, from the electromagnetic force that governs electricity and magnetism, to the strong nuclear force that binds quarks together in the heart of atoms. But while the Standard Model has been remarkably successful in explaining much about the universe at its smallest scales, it leaves many unanswered questions. For one, it does not explain gravity, which remains an enigma in the context of quantum mechanics. Furthermore, it offers no answers about dark matter and dark energy, mysterious substances that make up most of the universe's mass and energy, but remain elusive to direct detection. The search for answers in particle physics has driven the development of sophisticated technologies that have transformed our understanding of the universe. Particle accelerators such as the Large Hadron Collider, LHC, near Geneva, Switzerland, push the boundaries of scientific knowledge. These accelerators can smash particles together at nearly the speed of light, creating conditions that mimic the high-energy environments of the early universe, moments after the Big Bang. It was at the LHC that scientists discovered the Higgs boson, a fundamental particle that gives other particles their mass. This discovery was a monumental breakthrough in particle physics and filled a critical gap in our understanding of how the universe operates on its most basic level. Yet, even with the remarkable success of the Standard Model and the incredible breakthroughs made in particle physics, scientists are still searching for a more complete theory, one that can unify the forces of nature, including gravity, and provide answers to the cosmic mysteries of dark matter and dark energy. These questions lie at the heart of ongoing research, pushing the boundaries of our knowledge and inspiring the next generation of explorers in the scientific community. But particle physics is not the only field exploring the origins of the universe. Cosmology, the study of the universe as a whole, provides critical insights into how everything began and evolved. The Big Bang Theory, one of the most well-established models of the universe's origins, suggests that the universe began from a singular, incredibly hot and dense point about 13.8 billion years ago. From this moment, space itself began to expand, carrying with it the building blocks of matter and energy that would eventually form the galaxies, stars, and planets we observe today. Cosmology and particle physics are deeply interconnected. The study of the early universe relies on understanding how particles behaved at extremely high energies, similar to those that existed just fractions of a second after the Big Bang. By recreating these conditions in particle accelerators like the LHC, scientists can study the interactions that took place in the universe's infancy, offering a window into the fundamental processes that governed its creation. As we look to the future, the mysteries of dark matter and dark energy remain some of the most pressing questions in both cosmology and particle physics. Dark matter, though invisible to our instruments, can be detected through its gravitational effects on visible matter. It is thought to make up about 27% of the universe's mass energy content, yet its nature remains a complete mystery. Dark energy, an even more elusive force, is believed to be responsible for the accelerated expansion of the universe. Together, these two components constitute approximately 95% of the universe's total mass and energy, yet we know next to nothing about them. These mysteries, while perplexing, also present an opportunity, a challenge to scientists to develop new theories, new technologies, and new methods of exploration. As we continue to probe the deepest recesses of space and the tiniest particles that make up our world, we are reminded that the journey to understand the universe is not just about answering questions, it is about asking the right ones, and never ceasing to seek the answers that lie beyond the known, in the realm of the unknowable. Particle physicists are tirelessly searching for the elusive particles that might comprise dark matter, employing both underground detectors and space-based observatories to gather any signs of these mysterious entities. At the same time, cosmologists take these findings and integrate them into models that aim to explain the broader structure and behavior of the universe. The intersection of cosmology and particle physics has never been more evident, particularly through the study of cosmic microwave background radiation, a remnant from the Big Bang that offers a glimpse of the universe when it was just 380,000 years old, a time before stars and galaxies had begun to form. By meticulously analyzing the slight temperature variations within this radiation, scientists are able to extract valuable information about the distribution of matter and the early conditions that shaped the cosmos. These subtle fluctuations serve as a key to unlocking the universe's deep mysteries. They not only provide a snapshot of the universe's infancy, but also play a pivotal role in the development of both cosmology and particle physics. By studying the patterns within the cosmic microwave background, researchers can infer the properties of the fundamental forces and particles that govern the formation of the universe. In this way, the cosmic microwave background acts as a powerful link between the two fields, highlighting the way in which they inform and challenge one another. Such interdisciplinary investigations provide a fuller picture of our universe's origins, while also pushing the boundaries of established scientific theories. One of the most intriguing areas of intersection between cosmology and particle physics is the study of discrepancies in measurements of the Hubble constant, the rate at which the universe is expanding. These discrepancies suggest that there may be new physics at play, which are not fully explained by the standard model of particle physics or the lambda CDM model, the leading cosmological theory. This anomaly has become a key puzzle for scientists, one that drives the ongoing quest for a unified theory of everything. Such a theory would reconcile the laws governing the vast expanses of the universe with those dictating the behavior of subatomic particles, ultimately bridging the gap between cosmology and particle physics. Furthermore, to fully appreciate the profound relationship between these two fields, we must examine the fundamental forces of nature, the underlying principles that govern both the grand scale of the cosmos and the intricate world of subatomic particles. These forces serve as the universe's rulebook, shaping how all matter, from galaxies to elementary particles, interacts with one another. A deep understanding of these forces allows us to grasp everything from the movements of celestial bodies to the stability of atoms themselves. In total, there are 4 fundamental forces recognized by physicists: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces operates at different scales, exerting its influence over vast stretches of space or at the incredibly small subatomic level. Gravity, perhaps the most familiar force to us all, is the force that keeps our feet firmly planted on the Earth and dictates the motion of planets, stars, and galaxies. Despite its ubiquity, gravity is the weakest of the 4 forces, though its effects are felt across immense distances, from the orbit of planets to the curvature of spacetime itself. The gravitational force between 2 objects is determined by their masses and the distance between them, a relationship first described by Isaac Newton's law of universal gravitation. Albert Einstein's theory of general relativity further refined this view, proposing that gravity is not merely a force, but the curvature of spacetime caused by massive objects. Electromagnetism, on the other hand, is responsible for the vast majority of phenomena that we experience in our daily lives, especially at scales larger than the atomic level. This force operates between charged particles like protons and electrons and governs phenomena such as electricity, magnetism, and light. Compared to gravity, electromagnetism is significantly stronger at the particle level and plays an essential role in the structure of atoms, chemical bonding, and the transmission of signals in living organisms. The effects of electromagnetism are seen all around us, from the energy we use to power our homes to the chemical processes that sustain life. The strong nuclear force, or strong interaction, is the most powerful of the 4 forces, but it only acts over extremely short distances. This force binds protons and neutrons together within the nucleus of an atom, overcoming the electromagnetic repulsion between positively charged protons. Without the strong force, atoms as we know them could not exist. It also plays a crucial role in holding quarks together to form protons and neutrons, which are the building blocks of atomic nuclei. The weak nuclear force, though weaker than the strong force, is equally essential for the processes that fuel the universe. It is responsible for phenomena such as radioactive decay and nuclear reactions, including the processes that power stars like our sun. The weak force operates over an even shorter range than the strong force and facilitates the transformation of one type of subatomic particle into another, such as the conversion of a neutron into a proton, electron, and neutrino. This force is central to nuclear fusion, the process that powers the stars and facilitates the creation of elements that are vital for life. These 4 fundamental forces are central to the ongoing research that seeks to unify the vast and varied realms of cosmology and particle physics. Researchers continue to strive for a theory that will bring all 4 forces together into one cohesive framework. Despite significant advancements, a unified theory remains an elusive goal, one that could ultimately provide a deeper understanding of how the universe operates on both the grandest and most microscopic scales. As we look forward to the future, the intersection of cosmology and particle physics promises to yield new insights, pushing the boundaries of our knowledge and potentially rewriting our understanding of the universe itself. The search for a theory of everything continues to be one of the most ambitious and captivating quests in the world of physics, a theory that promises to reveal the ultimate secrets of our universe. As scientists delve deeper into the mysteries of the cosmos, their goal is to uncover a single, all-encompassing framework that unites every force, every particle, and every interaction in the universe. This pursuit drives much of today's groundbreaking research, offering a tantalizing glimpse into the very fabric of existence itself. But to truly understand the universe, we must first explore the smallest and most fundamental components that make up everything we see, feel, and experience. At the heart of this exploration are the particles that constitute matter, particles so small that they are beyond the reach of our naked eyes. These building blocks form the foundation of everything visible, from the air we breathe to the stars that light up the night sky. The standard model of particle physics provides the most widely accepted framework for understanding these particles, breaking them down into 3 categories: quarks, leptons, and the force carrier particles that mediate the fundamental forces of nature. Quarks, the tiniest of these particles, combine to form the protons and neutrons that make up atomic nuclei. There are 6 distinct types of quarks, often referred to as flavors: up, down, charm, strange, top, and bottom. Quarks are never found alone in nature due to a phenomenon known as color confinement. Instead, they always group together, either in pairs, mesons, or triplets, baryons. For example, protons are made up of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. The strong nuclear force, the most powerful force in the universe, binds these quarks together within atomic nuclei, holding them in a delicate yet unbreakable grip. Leptons, another essential family of particles, include the well-known electron. Like quarks, leptons come in 6 varieties: the electron, muon, tau, and their corresponding neutrinos: electron neutrino, muon neutrino, and tau neutrino. Unlike quarks, however, leptons are not affected by the strong nuclear force. Instead, they are governed by the electromagnetic and weak nuclear forces. Electrons, which orbit the nucleus of an atom, are crucial for chemical reactions and electrical conductivity, while neutrinos, almost ghost-like in their interaction with matter, travel through space, barely interacting with anything. These elusive particles are incredibly difficult to detect, but are produced in vast numbers by processes like nuclear fusion in the sun. Alongside quarks and leptons, the standard model also includes force carrier particles, or bosons, which mediate the 4 fundamental forces: gravity, electromagnetism, the strong force, and the weak force. Photons are the bosons responsible for carrying electromagnetic force. Gluons mediate the strong nuclear force, and W and Z bosons are involved in the weak force. Perhaps the most famous of these is the Higgs boson, discovered in 2012, which is associated with the Higgs field. This field is responsible for giving particles their mass, a fundamental property that influences the structure of the universe itself. As we move from the microscopic particles to the vast expanse of the universe, we enter the realm of cosmology, where the Big Bang theory reigns as the key to understanding the origin of the cosmos. The Big Bang theory proposes that approximately 13.8 billion years ago, the entire universe was concentrated in a single, infinitely dense and hot point. From this singularity, space itself began to expand rapidly, giving birth to the universe we observe today. Unlike an explosion which sends matter outward into empty space, the Big Bang was an expansion of space itself, a stretching of the very fabric of the cosmos. Imagine a balloon with dots representing galaxies. As the balloon inflates, the dots move away from each other, illustrating how galaxies move apart as the universe continues to expand. This visualization helps us understand the true nature of the Big Bang, showing that the expansion is not an outward explosion, but rather the stretching of space itself, carrying galaxies farther from one another as the universe grows. Evidence supporting the Big Bang theory is abundant and persuasive. One of the most compelling pieces of evidence comes from the discovery of cosmic microwave background (CMB) radiation in 1965 by Arno Penzias and Robert Wilson. This faint glow, which permeates the universe, is the afterglow of the Big Bang, stretched to microwave frequencies by the expansion of space. By studying the CMB, scientists are able to gain valuable insights into the early conditions of the universe, revealing its composition, temperature, and even its age. Another crucial piece of evidence comes from the observation of the redshift of light emitted by distant galaxies. As the universe expands, the space between galaxies also stretches, causing the light from these galaxies to shift toward longer, redder wavelengths. This phenomenon, first observed by Edwin Hubble in 1929, provides direct evidence that the universe is not static but ever expanding, confirming the predictions made by the Big Bang theory. The journey to understanding the universe, from the smallest particles to the grandest galaxies, is ongoing, with each new discovery bringing us closer to uncovering the ultimate truths that govern the cosmos. As we continue to investigate the very building blocks of matter and the origins of the universe, we are reminded that our quest for knowledge is not just about answering questions, but about exploring the very essence of existence itself. Furthermore, the Big Bang theory offers a profound explanation for the relative abundances of the lightest elements that populate our universe: hydrogen, helium, and lithium. These elements, formed in the first few minutes after the Big Bang through a process known as nucleosynthesis, remain a key piece of evidence supporting the theory. The proportions of these elements in the universe today align remarkably with the predictions made by the Big Bang model, reinforcing its scientific credibility. However, despite its widespread acceptance and the wealth of supporting evidence, the Big Bang theory is far from offering a complete understanding of the cosmos. It leaves numerous mysteries unexplored, especially in regard to dark matter and dark energy. These elusive entities make up the majority of the universe's mass energy content, but remain invisible and undetectable, defying explanation. Additionally, the Big Bang theory offers no answers to the ultimate questions. What existed before the Big Bang? What sparked the initial expansion? These gaps leave ample room for continued scientific inquiry and exploration. The Big Bang theory has fundamentally transformed our view of the universe, offering an elegant narrative that spans the origins, structure, and evolution of the cosmos. It paints a dramatic picture of a universe that began as a single, infinitely dense point, unimaginably hot and packed with energy. Over billions of years, this primordial singularity has evolved into the vast, intricate universe we observe today, complete with galaxies, stars, and planets. But to understand this evolutionary journey, we must first look back to the universe's fiery infancy. In the immediate aftermath of the Big Bang, the universe was a seething mass of energy and radiation, so hot and dense that matter, as we understand it, could not yet form. Instead, the universe was dominated by a quark-gluon plasma, a state where quarks, the fundamental building blocks of protons and neutrons, and gluons, the force carriers binding quarks together, moved freely in a hot, dense soup. This soup was the very foundation of matter as we know it. As the universe expanded, it began to cool, marking the beginning of the slow process of forming stable matter. Within the first microseconds, the universe cooled enough for quarks to combine into protons and neutrons, marking the start of the Hadron epoch. This pivotal moment set the stage for the universe's first nuclei to form during nucleosynthesis, just a few minutes after the Big Bang. The nuclei of hydrogen, deuterium, a stable isotope of hydrogen, helium, and trace amounts of lithium emerged, forming the first building blocks of matter. The precise ratios of these light elements, predicted by the Big Bang nucleosynthesis model, closely mirror what we observe in the universe today, providing strong empirical support for the theory. Yet the universe was still far too hot for electrons to join these nuclei and form neutral atoms. It wasn't until around 380,000 years after the Big Bang, during a crucial period known as recombination, that the temperature dropped sufficiently for electrons to combine with nuclei and form the first neutral atoms. This momentous shift marked a turning point in the universe's evolution. It allowed light to travel freely through space for the first time, illuminating the cosmos and releasing the cosmic microwave background radiation, an ancient snapshot of the universe in its infancy. The CMB provides irrefutable evidence of the Big Bang, offering a window into the universe's early conditions. The formation of these neutral atoms set the stage for the development of stars and galaxies. Gravity, now able to exert its influence, began to pull matter together, forming dense gas clouds. These clouds became the birthplaces for the first stars, which, through nuclear fusion, began to forge heavier elements in their cores. These newly synthesized elements enriched the universe's chemical diversity, laying the groundwork for the formation of planets and life as we know it. The evidence supporting the Big Bang theory not only confirms that the universe originated from a singular, intensely hot and dense point, but also provides a detailed understanding of the universe's evolution over billions of years. From the formation of the lightest elements to the cooling of matter, the expansion of space, and the emergence of the first stars, the theory tells a coherent, scientifically grounded story of cosmic development. This evidence is invaluable, offering not just a glimpse into the past, but also guiding our future explorations of the universe. One of the most compelling pieces of evidence for the Big Bang theory is the cosmic microwave background radiation, CMB. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is a faint, pervasive glow of light that fills the universe. This radiation, a remnant from the universe's earliest moments, was emitted when the universe cooled enough for atoms to form and light to travel freely. Over the billions of years since, the expansion of the universe has stretched this radiation into the microwave range, providing scientists with a snapshot of the universe just 380,000 years after the Big Bang. And the CMB is a vital piece of evidence that not only affirms the Big Bang model, but also serves as a powerful tool for studying the universe's infancy and understanding its origins. In the quiet expanse of the universe, satellites like COBE, WMAP, and Planck have been our eyes, capturing the echoes of the universe's birth. They've measured the cosmic microwave background CME radiation with astounding precision, offering us a detailed portrait of the early cosmos. These measurements revealed faint temperature fluctuations, tiny ripples that signify variations in density, and these initial fluctuations were the building blocks of everything we see today: galaxies, stars, and planets. These subtle variations serve as the fingerprints of the universe's infancy, holding the key to its grand evolution. This evidence of cosmic fluctuation aligns with the Big Bang theory, suggesting that the universe began in a state of intense heat and density. As the universe expanded, it cooled, leading to the formation of the structures we now observe. The expansion itself, an ongoing process, serves as a direct testament to the explosive origin of the cosmos. But how do we know this expansion is real? In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He observed that galaxies scattered across the heavens were receding from us, and the speed at which they moved away was directly proportional to their distance. This pivotal observation, known as Hubble's law, suggested an expanding universe, reinforcing the notion that the universe must have been far smaller and denser in the past, exactly as the Big Bang theory predicts. This expansion, far from being a mere curiosity, is a dynamic narrative that reveals the universe's explosive birth. In its very fabric, we see its early, fiery origins. But there's more to the story. The Big Bang theory also predicts the creation of the universe's lightest elements in the first few minutes after the Big Bang, in a process known as primordial nucleosynthesis. Hydrogen, helium, and trace amounts of lithium were produced during this fleeting period. And when we examine the universe today, we find that the abundance of these elements precisely matches the predictions of the Big Bang theory, confirming that the universe once existed in a dense, hot state, ripe for the formation of these fundamental building blocks. As we expand our view, the structure of the universe emerges in unexpected ways. Galaxies are not scattered haphazardly across the cosmos. They form vast webs of filaments and voids. These structures are not random. They are a natural consequence of gravitational forces acting on the early fluctuations in the universe's density. The way galaxies are distributed across the cosmos, from dense clusters to empty voids, mirrors the Big Bang theory's predictions, offering yet another clue in the cosmic puzzle. These galaxies are the living proof of the universe's history, and their placement and movements trace the path laid out in the early moments of the universe's existence. Continuing our exploration, we journey deeper into the microscopic realm, where the laws of quantum mechanics govern the cosmos at its most fundamental level. Here, quantum fluctuations rule. These fluctuations, driven by the uncertainty principle articulated by Werner Heisenberg, are a cornerstone of quantum mechanics. According to this principle, certain pairs of physical properties, such as the position and momentum of a particle, cannot both be precisely measured at the same time. This inherent uncertainty is not just a curiosity, it's a fundamental feature of the quantum world. In what we perceive as the vacuum of space, empty space, seemingly devoid of matter, quantum fluctuations constantly occur. Particles and antiparticles appear and vanish in the blink of an eye, creating and annihilating themselves in a continuous dance. These fleeting particles, known as virtual particles, are an intriguing manifestation of the quantum realm. Though they exist only for brief moments, they leave real impacts, influencing the behavior of other particles. For example, quantum fluctuations can alter the energy levels of electrons within atoms, an effect that has been observed and verified in laboratory experiments. But these tiny, transient events aren't merely a curiosity. They played a significant role in shaping the universe itself. During the period of cosmic inflation, an incredibly rapid expansion of the universe just moments after the Big Bang, these quantum fluctuations were stretched across vast scales. In this process, what began as tiny, microscopic variations in the density of the universe grew to become the large-scale structures, galaxies, and clusters of galaxies that define the universe as we know it. This stretching, a profound event in the history of the cosmos, directly influenced the distribution of matter across the universe, and it left an indelible mark on the cosmic microwave background radiation, offering us a glimpse into the quantum origins of the universe itself. At the core of these fluctuations lies the Heisenberg uncertainty principle. This principle tells us that even in the emptiness of space, there is no true vacuum. It is filled with the fleeting existence of virtual particles. These particles pop into and out of existence, borrowing energy from the surrounding space only to annihilate each other in a blink of an eye. While these particles may not be directly observed, they are integral to the functioning of the universe, contributing to the dynamic forces at play on a quantum scale. But the implications of quantum fluctuations go beyond the theoretical. They can lead to the creation of real particles under certain conditions. One such scenario occurs near the event horizon of a black hole, where quantum fluctuations give rise to a phenomenon known as Hawking radiation. This radiation, predicted by physicist Stephen Hawking, suggests that black holes can emit particles as a result of quantum fluctuations, slowly evaporating over time. The idea of Hawking radiation has profound implications for our understanding of black holes and the fundamental nature of the universe, connecting the quantum world to the cosmological scale in ways previously thought impossible. Thus, the universe, from its earliest moments to its present state, is a tapestry woven from the threads of quantum mechanics, cosmic inflation, and the Big Bang. Each of these elements plays a crucial role in shaping the world we inhabit, and the story of the universe's creation is one of astonishing complexity and beauty. Through satellites like COBE, Double Map, and Planck, we have only begun to scratch the surface of this extraordinary tale, offering us a glimpse into the mysterious depths of the cosmos. In the vast depths of our universe, Stephen Hawking proposed a groundbreaking idea. Quantum fluctuations at the edge of a black hole might give birth to particles. These fluctuations, at the very threshold of a black hole's event horizon, could lead to the creation of particle-antiparticle pairs. One particle would fall into the abyss, while the other would escape into the cosmos. This remarkable process allows for the creation of real particles from the vacuum itself, a phenomenon so profound that it leads to the black hole's eventual loss of mass over time as the escaping radiation chips away at its core. But the dance of quantum fluctuations doesn't end at black holes. Another critical chapter in the story of the universe's origins is the period known as cosmic inflation. This theory proposes that just moments after the Big Bang, the universe expanded at an extraordinary rate, stretching quantum fluctuations to unimaginable scales. These once microscopic fluctuations were magnified to cosmic proportions, serving as the foundation for the structures we observe today: galaxies, galaxy clusters, and the very fabric of the universe itself. During this inflationary period, the quantum fluctuations, originally tiny ripples in space-time, were frozen into real particles. These particles, created from the primordial energy of the universe, played an essential role in the birth of matter. This quantum phenomenon is not just an abstract curiosity, it's an essential mechanism for the formation of the universe as we know it, with energy directly shaping the evolution of cosmic structures. This interconnection between quantum mechanics and cosmology reveals a beautiful paradox. The invisible, minute processes at the quantum level directly influence the formation of the universe's grandest structures. Now let's dive even deeper into this realm. The very essence of particle formation hinges on energy. Quantum fluctuations, as fleeting as they may seem, are powered by energy, transforming the void into a hotbed of potential. It is through energy that these fluctuations manifest into real, observable particles. This connection between energy and mass is beautifully encapsulated in Einstein's iconic equation, E equals mc squared, where energy E and mass m are two sides of the same coin, and c represents the speed of light. In the quantum vacuum, what appears to be nothingness is in fact a seething cauldron of potential energy, where virtual particles come to life. In the early universe, energy was the foundation of everything. After the Big Bang, the cosmos was a furnace of extreme heat and density, a place where energy was transformed into matter. As the universe expanded and cooled, energy began to condense, forming the very particles that would later combine to create atoms, stars, and galaxies. The early universe saw this transformation in phases, the electroweak epoch and the quark epoch, where the fundamental forces of nature began to separate and the building blocks of matter took form. The conversion of energy into particles is not only crucial for understanding the origins of the universe, but it also continues to shape the cosmos in profound ways. Energy governs the interactions of particles and dictates the structure of matter. For instance, the energy released during nuclear fusion in the hearts of stars fuels the synthesis of the heavier elements essential for life, from carbon to iron. This same energy powers the processes that drive stellar evolution and the creation of all elements, highlighting the pivotal role energy plays in the cosmic narrative. As we explore the creation of particles, we are inevitably drawn to another cornerstone of quantum mechanics, the Heisenberg uncertainty principle. This principle, introduced by Werner Heisenberg in 1927, unveils the inherent fuzziness of the quantum world. It tells us that we can never know both the exact position and the exact momentum of a particle at the same time. This fundamental uncertainty is not just a mathematical oddity, it's a reflection of the very nature of reality at the quantum level. It also has profound implications for particle creation, as the limitations on our ability to measure quantum states allow fluctuations to emerge, giving rise to real particles from the vacuum. In essence, the creation of particles from quantum fluctuations is a beautiful manifestation of the universe's deepest secrets. It ties together the realms of quantum mechanics and cosmology, demonstrating how the smallest phenomena can have far-reaching consequences in the structure of the cosmos. The energy that powers these fluctuations, the uncertainty that governs their existence, and the massive scale at which they occur all come together to paint a portrait of the universe as a living, breathing entity, constantly evolving from the most microscopic to the grandest scales. The universe, it turns out, is a place where the line between the quantum and the cosmic is not as clear as we might think. But as the universe expanded and cooled, the forces began to separate, each one carving its distinct path in the evolution of the cosmos. This dramatic unfolding of forces is integral to our understanding of the universe's early development and marks the beginning of the formation of the very fabric of reality. At first, in the first microseconds after the Big Bang, all the fundamental forces, gravitational, electromagnetic, weak nuclear, and strong nuclear, were unified as a single force due to the extraordinarily high temperatures and densities. This period, known as the Grand Unification Epoch, was characterized by conditions so extreme that all the forces of nature were indistinguishable from one another. However, as the universe cooled, these forces gradually began to separate, each force taking on its unique properties. The first to split was the strong nuclear force, followed by the electroweak force, a merger of the electromagnetic and weak nuclear forces. This moment of separation, known as symmetry breaking, was a pivotal event in the universe's infancy, shaping the nature of the cosmos as we know it. The cooling of the universe allowed these forces to evolve into their present forms, setting the stage for the formation of particles and the dynamics of the universe. Simultaneously, as the universe cooled, the creation of particles continued. The uncertainty principle, a cornerstone of quantum mechanics, played a significant role in this process. As virtual particles spontaneously appeared and annihilated within the vacuum, they began to influence the formation of real particles. In extreme conditions, near the event horizon of black holes or during the rapid expansion of the early universe, these virtual particles could be separated and become real. This phenomenon of particle creation helped fill the early universe with matter, providing the building blocks for everything that would come after. As the universe cooled even further, we entered the Hadron epoch. For a brief period, just microseconds to seconds after the Big Bang, the universe was a seething soup of quarks and gluons. These quarks, the fundamental building blocks of matter, were not yet bound together into protons and neutrons. Instead, they existed freely in this state of matter, known as quark-gluon plasma. As the universe expanded and cooled, quarks began to combine, forming protons and neutrons, the very foundation of atomic nuclei. In the aftermath of the Hadron epoch, the universe moved into the lepton epoch, where leptons like electrons became the dominant form of matter. Despite the cooling, conditions were still too hot for protons and neutrons to combine and form stable atomic nuclei. The universe continued to cool, and eventually it reached a crucial point, nucleosynthesis. This period, just minutes after the Big Bang, saw protons and neutrons come together to form the nuclei of the simplest elements, hydrogen, helium, and trace amounts of lithium and beryllium. This era of primordial nucleosynthesis was the birthplace of much of the helium in the universe, alongside the hydrogen that didn't fuse into helium nuclei. However, even as these atomic nuclei formed, the universe was still too hot for electrons to be captured by these nuclei, preventing the formation of neutral atoms. It wasn't until about 380,000 years later, during the epoch of recombination, that the universe cooled sufficiently for electrons to be captured into orbits around atomic nuclei. This allowed the formation of neutral atoms, leading to the decoupling of matter and radiation and the release of the cosmic microwave background radiation. This radiation, which still permeates the universe today, provides us with a snapshot of the universe's state at that moment, an invaluable tool for understanding the early universe. As we venture deeper into the history of the universe, we witness the continued evolution of the fundamental forces and particles that would eventually give rise to the galaxies, stars, and planets we observe today. The narrative of separation and distinction of these forces forms a cornerstone of our understanding of the cosmos. From the primordial soup of quarks and gluons to the formation of atoms and the cosmic background radiation, these events set in motion the vast and intricate universe we now explore. As the universe expanded and cooled, what was once a unified primordial state began to unravel through a series of symmetry-breaking events. These fractures marked the creation of the fundamental forces we know today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity was the first to emerge as a distinct force, carving out its own existence just moments after the Big Bang. At this stage, the universe was in an intensely hot and dense state, and gravity's separation from the rest of the forces marked the universe's first step toward the complex web of interactions that would define its future. Gravity's decoupling also played a crucial role in shaping the cosmic structure, guiding the formation of galaxies, stars, and planets, and laying the very foundation for the universe as we know it. Following the separation of gravity, the universe continued to cool, and the grand unified force, which had once encompassed both the electromagnetic and nuclear forces, began to break apart as well. The strong nuclear force responsible for binding quarks within protons and neutrons finally distinguished itself from the electroweak force, a union of the electromagnetic and weak nuclear forces. This separation, which occurred around 10^36 to 10^32 seconds after the Big Bang, during the epoch of cosmic inflation, set the stage for the formation of the first particles in the universe. The strong nuclear force, with its immense power, would go on to hold together the building blocks of matter, while the electroweak force continued to dominate the early universe's energetic landscape until it too underwent a critical symmetry-breaking event. This event, occurring around 10^12 seconds after the Big Bang, split the electroweak force into the electromagnetic force, mediated by photons, and the weak nuclear force, governed by W and Z bosons. The emergence of these distinct forces marked the universe's maturation, paving the way for the eventual formation of more complex particles, and ultimately, atoms. These critical phases of separation, gravity's decoupling, the differentiation of the strong and weak nuclear forces, and the final delineation of the fundamental forces, were instrumental in the universe's evolution, fostering the diversity of matter and the cosmic structures we observe today. As we move further into the history of the universe, we encounter the electroweak epoch, a period of immense significance in shaping the cosmos. This epoch, occurring between 10^12 seconds and 10^6 seconds after the Big Bang, was a time when the universe remained in a hot, dense, and dynamic state. However, as it continued to cool, it reached a critical point where the unified electroweak force underwent a crucial symmetry breaking event. This process led to the separation of the electromagnetic and weak nuclear forces, each with its own distinct role in the universe's evolution. The electroweak epoch is not only vital for understanding the early universe, but it also plays a key role in particle physics, particularly in the Standard Model. During this epoch, the universe was filled with a hot, dense plasma of quarks, leptons, and their antiparticles. The electroweak bosons, responsible for mediating the forces, filled the universe, helping govern the interactions of the particles. As the universe expanded and cooled further, the forces underwent their transformations, eventually allowing for the creation of the diverse array of particles that would form the building blocks of matter. A major player in this epoch was the Higgs mechanism, a process that involved the interaction of particles with the Higgs field, endowing them with mass. This was a pivotal step in the separation of the electromagnetic and weak forces, and the discovery of the Higgs boson in 2012 provided crucial evidence supporting this theory. The Higgs field's influence during the electroweak epoch was essential for the development of the Standard Model and our understanding of particle physics. The Higgs mechanism not only provided mass to fundamental particles, but also played a foundational role in shaping the universe's evolution. Quarks, the very building blocks of matter, were directly influenced by the strong nuclear force during this period. This force, which is incredibly powerful but acts over an extremely short range, began its work in the early universe, binding quarks together in triplets to form baryons, the constituents of protons and neutrons. These baryons would go on to form atomic nuclei, setting the stage for the development of atoms and the chemical elements that would define the universe's matter. The strong nuclear force's power was instrumental in creating the structures we observe within atoms and throughout the cosmos. Thus, the electroweak epoch and the separation of the fundamental forces are not mere historical events in the universe's infancy. They represent critical moments in the shaping of the universe's structure and the particles that make up all matter. Without these early transformations, the universe would not have been able to cool sufficiently to allow for the formation of complex particles, atoms, and eventually the galaxies, stars, and life forms that exist today. The story of the universe's evolution is one of deep, intricate connections between fundamental forces, particle interactions, and the delicate balance of energy and matter that has shaped the cosmos we live in. The process began when the universe cooled enough for the strong force to overcome the tremendous kinetic energy that had previously kept quarks separated. In this still, searing hot environment, quarks began interacting more closely, forming pairs known as quark-antiquark pairs and triplets, which would eventually evolve into protons and neutrons. These fundamental particles, protons composed of 2 up quarks and 1 down quark, and neutrons made of 2 down quarks and 1 up quark, would become the building blocks of matter. As the temperature decreased, quarks, previously free to roam in a state known as quark-gluon plasma, began to lock into protons and neutrons. This transition was no small feat. It marked a crucial turning point in the evolution of the cosmos. The locking of quarks within protons and neutrons made the formation of stable matter possible, something that would otherwise have been impossible. Without this process, the complex structures of atoms, stars, and galaxies as we know them could never have emerged. The quarks, once able to move independently, were now bound together in a manner that would underpin the very fabric of the universe. This phase, the hadronization of quarks into protons and neutrons, was an essential precursor to the next monumental chapter of the universe's evolution: nucleosynthesis. It was here, as the universe continued to expand and cool, that the stage was set for the fusion of protons and neutrons into the nuclei of the simplest elements. About 3 minutes after the Big Bang, temperatures had dropped enough to allow these nuclear forces to overcome the electromagnetic repulsion between protons, causing them to fuse with neutrons. It was during this momentous period that the first atomic nuclei took form. Most notably, hydrogen nuclei, protons, fused to form helium, while trace amounts of deuterium, heavy hydrogen, tritium, a radioactive form of hydrogen, and very small quantities of lithium and beryllium were also produced. The process of nucleosynthesis was not just a moment of cosmic creation. It was a pivotal turning point in the universe's evolution. This event not only set the initial abundances of the light elements, but also provided vital evidence supporting the Big Bang theory. The ratios of hydrogen and helium seen in the present universe closely match the predictions made by the theory, adding a critical piece to the puzzle of our cosmic origin. These primordial elements, formed in the furnaces of the early universe, would go on to play a central role in the formation of stars, which, through their own nuclear fusion processes, would eventually produce the heavier elements necessary for life and the complex structures we see today. The importance of nucleosynthesis extends far beyond just the formation of atomic nuclei. It represents the universe's first steps toward chemical diversity, transforming from a world of simple particles and forces into a realm filled with matter. These early elements would later combine and undergo further fusion in stars, eventually leading to the rich variety of elements that make up the planets, life, and all the celestial bodies around us. As the universe continued to cool, it began to evolve from a state dominated by simple particles into a realm of growing complexity. However, it would take another pivotal moment for the universe to take its next giant leap forward, the formation of the first atoms. Around 380,000 years after the Big Bang, the universe had cooled sufficiently for electrons to combine with atomic nuclei, forming neutral atoms in an event known as recombination. This period, set against the backdrop of an ever-expanding and cooling universe, marked the birth of atomic matter as we understand it. The cooling allowed protons and neutrons, previously formed in the earlier stages of nucleosynthesis, to bind with electrons, creating the first simple atoms. These atoms primarily consisted of hydrogen, with small amounts of helium, deuterium, and lithium. While these were the simplest and most abundant elements, their formation would have far-reaching consequences. At the time of recombination, the universe was still too hot for electrons to remain bound to atoms for long periods. As a result, the universe remained in a state known as a free electron plasma. In this state, electrons were not able to form stable orbits around atomic nuclei, and instead scattered freely. This prevented the photons, light particles, from traveling freely, making the universe opaque. The scattering of photons and the state of free electron plasma were the reasons the universe remained in this opaque, foggy condition until later. Ultimately, the transition from a free electron plasma to a universe of neutral atoms set the stage for the next monumental leap forward in the cosmic story, one that would eventually lead to the formation of stars, galaxies, and all the fascinating structures we observe across the universe. As the universe continued to expand and cool, it reached a critical point. At this moment, the energy of the photons could no longer ionize hydrogen atoms. Electrons began to combine with hydrogen and helium nuclei, forming the very first stable atoms. This process, known as recombination, marked a dramatic shift in the universe's behavior. With atoms now formed, photons could travel freely without constant scattering. For the first time, the universe became transparent, allowing light to travel across vast distances. The photons released at this moment are still detectable today, forming the cosmic microwave background radiation, a relic of the universe's infancy, offering us a glimpse into the state of the cosmos during this pivotal event. This formation of the first atoms wasn't just a milestone, it was a turning point in the cosmic story. It ushered in a new era for the universe, transitioning it from a hot, dense state to a cooler and more structured one. This shift made it possible for more complex structures, such as stars and galaxies, to form. Recombination marked the end of the universe's dark ages, a time when the cosmos was devoid of visible light, as no stars had yet ignited. It also set the stage for the gravitational collapse of matter, eventually leading to the birth of the first stars and galaxies. These early stars would play a crucial role in enriching the universe with heavier elements, a process known as stellar nucleosynthesis. Through stellar nucleosynthesis, stars created the diverse array of elements that now populate the universe. The elements formed in the earliest stars laid the groundwork for the rich complexity of the universe that we observe today. From the most basic elements like hydrogen and helium, the process of nucleosynthesis created an expanding variety of elements crucial for the formation of planets and life itself. Nucleosynthesis within stars transformed the simple ingredients of the early universe into the complex materials necessary for life. This cosmic furnace acted as the factory for chemical diversity, forging elements across multiple stages of the universe's history. It began with the Big Bang, which produced the lightest elements: hydrogen, helium, and trace amounts of lithium and beryllium. However, this early phase could only account for a fraction of the elements that make up the universe today. The next phase of nucleosynthesis occurred within the stars themselves, acting as the true factories for the creation of heavier elements. Inside a star's core, hydrogen nuclei fuse to form helium, a process known as hydrogen burning. As a star ages and its core becomes hotter and more massive, it begins to fuse helium into carbon. In more massive stars, the fusion process continues, forming progressively heavier elements through stages of nuclear burning, such as carbon, neon, oxygen, and silicon burning. However, the production of elements heavier than iron requires an entirely different set of conditions. Fusion within stellar cores cannot produce elements beyond iron due to the immense energy needed. Instead, these heavier elements are created in extreme events like supernova explosions or within the outer shells of asymptotic giant branch, AGB, stars. The creation of elements heavier than iron takes place through processes such as the R process and S process. The R process, or rapid neutron capture, occurs during supernova explosions. Here, a dense flux of neutrons is absorbed by atomic nuclei, leading to the creation of many of the heaviest elements in the periodic table. On the other hand, the S process, or slow neutron capture, occurs in the more stable environment of AGB stars. Neutrons are captured at a slower rate, creating elements like barium and lead. Both of these processes play vital roles in producing the diversity of elements necessary for the complex chemistry we observe in the universe. Once these elements are formed, they are released into the interstellar medium by stellar winds and supernova explosions. These explosions seed the galaxy with the raw materials needed for the next generation of stars, planets, and, eventually, life. Over billions of years, this cycle of stellar birth, nucleosynthesis, and death has enriched the cosmos with a rich chemical tapestry. Each generation of stars builds upon the elements created by the previous ones, leading to a universe filled with diverse elements, each playing a critical role in the formation of new stellar systems. As humanity has ventured into the realm of particle accelerators and experimental physics, we have come closer to understanding the very processes that shaped the cosmos. Particle accelerators, advanced machines that propel charged particles to extreme speeds, simulate the conditions that existed just after the Big Bang. By smashing particles together, scientists recreate the intense energy and temperatures that were present in the early universe, helping us better understand how the elements were formed and how they continue to influence the structure of the universe today. In the pursuit of understanding the universe, particle accelerators stand as one of humanity's most extraordinary achievements. By pushing the boundaries of science, these groundbreaking tools allow researchers to investigate the fundamental properties of matter and explore the forces that govern the interactions between subatomic particles. With the ability to accelerate particles to nearly the speed of light and collide them at high energies, particle accelerators break down atomic structures, revealing an intricate world of particles and phenomena that would otherwise remain hidden from view. The very operation of these remarkable machines involves the use of electric fields to accelerate particles and magnetic fields to steer and focus them along a carefully controlled path. The path itself can be circular, as seen in synchrotrons and storage rings, or linear, as in linear accelerators, LINACs. When these high-energy particles collide, the results are often extraordinary, generating new particles that open the door to the deepest questions of physics. These collisions recreate conditions akin to those that existed immediately after the Big Bang, enabling scientists to study the fundamental forces and building blocks of the universe under extreme energy densities. Across the globe, numerous particle accelerators serve different purposes, each contributing to our growing understanding of the cosmos. One of the most notable is the Large Hadron Collider, LHC, located at CERN near Geneva, Switzerland. As the world's largest and most powerful particle accelerator, the LHC is a beacon of modern science, designed to probe the universe's deepest mysteries. Through this enormous collider, scientists aim to explore the properties of the elusive Higgs boson, probe the enigmatic nature of dark matter, and answer fundamental questions about the very fabric of reality. Yet, particle accelerators do not exist solely to solve the grand mysteries of the universe. These machines are also practical tools that have found applications in fields as diverse as medicine, industry, and even art. In the realm of healthcare, particle accelerators play a crucial role in cancer treatment, particularly in radiation therapy. They also produce isotopes used in medical diagnostics, offering invaluable insight into the workings of the human body. In industry, accelerators assist in materials processing and semiconductor production, driving technological advancements. Even in the world of art and archaeology, these machines have proven indispensable, enabling scientists to analyze paintings and ancient artifacts without causing any damage, preserving precious cultural heritage for future generations. The development and operation of particle accelerators are feats of engineering and physics, requiring an extraordinary fusion of superconducting magnets, vacuum systems, and particle detection technologies. These tools, which have made it possible to explore the deepest questions of physics, are not just instruments of discovery, but also catalysts for technological innovation. They push the limits of what is possible, driving progress in a wide range of fields, from medicine to engineering, and contributing to the infrastructure that underpins modern society. Among the most significant contributions of particle accelerators to our understanding of the universe is the discovery of the Higgs boson. This particle, often referred to as the God particle, was first detected in 2012 by scientists at CERN's LHC. The discovery confirmed the existence of a particle predicted by the Standard Model of particle physics and provided the missing link in our understanding of why other particles have mass. This monumental achievement not only confirmed a key aspect of particle physics, but also earned Francois Englert and Peter Higgs the Nobel Prize in Physics in 2013, marking a defining moment in the field. However, the importance of particle accelerators extends far beyond the discovery of the Higgs boson. These machines were instrumental in confirming the existence of quarks, the fundamental building blocks of protons and neutrons. In the late 1960s and early 1970s, experiments at the Stanford Linear Accelerator Center, FLAC, provided the first direct evidence of quarks, solidifying the quark model and expanding our understanding of the structure of matter. Moreover, particle accelerators have opened new frontiers in the study of antimatter, the counterpart to regular matter. Experiments conducted at CERN and other research facilities have enabled scientists to create and trap antimatter particles, such as antihydrogen, offering valuable insights into the symmetries of the universe. These studies are critical in addressing some of the most profound questions in physics, such as why the universe is composed primarily of matter, despite the Big Bang Theory predicting equal amounts of matter and antimatter. As researchers continue to use particle accelerators to explore the most fundamental aspects of the universe, they also uncover new particles and forces that deepen our understanding of the cosmos. The discovery of W and Z bosons, for example, revealed the particles responsible for the weak nuclear force, which governs radioactive decay. Each breakthrough, whether it be the identification of a new subatomic particle or a deeper understanding of the fundamental forces, brings us closer to unraveling the mysteries of the universe, cementing particle accelerators as indispensable tools in the ongoing quest for knowledge. Through these incredible machines, humanity is not merely witnessing the universe unfold at the smallest scales. Particle accelerators are helping us to become active participants in uncovering the very building blocks that make up everything around us. The discovery of particles at CERN in the 1980s was nothing short of revolutionary, providing critical proof for the electroweak theory, a groundbreaking theory that unifies two fundamental forces, the electromagnetic and weak forces. This discovery was a monumental achievement in the quest to develop a unified theory of all the fundamental forces of nature. It marked a key milestone in our understanding of the universe, confirming that the forces governing particles at the subatomic level could indeed be linked in a way previously imagined only in theoretical models. Yet, the impact of particle accelerators stretches far beyond just fundamental physics. These accelerators have been instrumental in the development of life-saving medical technologies, like cancer therapy using particle beams. Their applications don't stop at the laboratory door. One of the most profound technological advances that emerged from CERN's experiments was the creation of the World Wide Web. Initially designed to help scientists share information seamlessly, this technology has now transformed the entire world. In fact, the discoveries at CERN and similar particle physics facilities have created a ripple effect, propelling advancements that touch nearly every aspect of modern life. But how exactly do these groundbreaking experiments validate the theoretical predictions that form the foundation of our scientific understanding? The process of validating theoretical predictions in particle physics is an intricate and deeply collaborative dance between theory and experiment. Theoretical physicists use mathematical models to explain the properties and behaviors of subatomic particles, often making predictions about phenomena that might not yet be observed. These models provide a framework for understanding how the forces of the universe interact at the smallest scales, and they suggest that there are particles yet to be discovered, phenomena yet to be explained. Once these predictions are made, it's up to experimental physicists to test them. Using particle accelerators, these scientists push particles to incredibly high energies, recreating conditions that mimic those of the early universe, mere moments after the Big Bang. They then collide these particles at incredible speeds, generating conditions so extreme that particles break apart or interact in ways that can only be captured through sophisticated detectors. These detectors, massive in scale and complexity, record the particles produced by these collisions, and the resulting data must be carefully analyzed to uncover the insights hidden within. To truly validate theoretical predictions, the results of these experiments must be reproducible. This means that not only must multiple experiments be conducted in different facilities around the world, but these experiments must also observe the same phenomena under similar conditions. When this happens, the credibility of the findings grows exponentially. Reproducibility in science is one of the most important ways to distinguish genuine discoveries from mere statistical anomalies or experimental errors. One of the crowning achievements in this ongoing effort is the Standard Model of Particle Physics, a theory that describes 3 of the 4 fundamental forces of nature: electromagnetic, weak, and strong nuclear forces, and classifies all known elementary particles. It is often described as the best framework we have for understanding the fundamental workings of the universe, encompassing everything from the particles that make up atoms to the forces that govern their interactions. It emerged over decades of research thanks to the work of physicists from around the globe and represents a synthesis of quantum mechanics and special relativity, unified into what is known as quantum field theory. The Standard Model divides elementary particles into 2 primary categories: fermions and bosons. Fermions, which include particles like electrons and the quarks that make up protons and neutrons, are the building blocks of matter. On the other hand, bosons are the force carriers. Photons, for example, carry the electromagnetic force, while gluons mediate the strong nuclear force. One of the most significant triumphs of the Standard Model was the prediction of the Higgs boson, a particle that provides mass to other particles through what is known as the Higgs mechanism. When the Higgs boson was discovered in 2012 at CERN's Large Hadron Collider, it confirmed a crucial component of the Standard Model and was hailed as one of the most significant achievements in modern physics. However, despite its immense successes, the Standard Model is far from complete. It leaves out the 4th fundamental force, gravity, described by Einstein's theory of general relativity. It also fails to account for the mysterious phenomena of dark matter and dark energy, which together make up most of the universe's mass energy content. Furthermore, the Standard Model doesn't explain the masses of elementary particles with full precision, and it cannot incorporate the gravitational force into the same framework. These gaps suggest that there is still a deeper, more comprehensive theory of the universe yet to be discovered, a theory that could one day unify all 4 fundamental forces into one elegant description. While the Standard Model has been remarkably successful in explaining much of the universe's particle interactions, it is clear that our understanding of the universe is still incomplete. It's as though we've uncovered a rich tapestry of the cosmos, but some threads remain missing, waiting to be woven into the broader picture by future discoveries. And so the search continues, pushing the boundaries of human knowledge ever forward, toward a more unified understanding of the fundamental forces that shape everything around us. But the limitations of the Standard Model stretch far beyond these. They not only delineate the current boundaries of physics, but also reveal the vast, uncharted territories waiting for discovery. These gaps hint at the presence of new physics, offering a roadmap for researchers intent on pushing the boundaries of knowledge and understanding the very fabric of the universe. One of the most glaring limitations is the failure of the Standard Model to incorporate gravity. Gravity, which governs the cosmos on the grandest scales, from planetary orbits to the evolution of galaxies, is described by Einstein's theory of general relativity. Yet the Standard Model, grounded in quantum field theory, offers no framework to include gravity. This creates an inherent disconnect between the realm of the extremely small, quantum mechanics, and the incredibly vast, general relativity. The inability to unite these two pillars of physics presents one of the most profound challenges faced by scientists today. The quest for a quantum theory of gravity, one that could harmonize quantum mechanics with general relativity, remains at the forefront of theoretical physics. Additionally, the Standard Model remains silent on two of the most mysterious and elusive components of the universe: dark matter and dark energy. Although we cannot directly observe dark matter, we know it comprises about 85% of the total mass in the universe. It neither emits nor absorbs light, and its presence is only inferred from its gravitational effects on visible matter. Likewise, dark energy, which makes up about 68% of the universe's energy content, is thought to drive its accelerated expansion. Despite their massive influence on the universe, the Standard Model offers no explanation for the nature of these forces. Their mysterious existence points to a need for a deeper understanding far beyond the scope of the current model. Furthermore, the Standard Model is unable to explain the striking imbalance between matter and antimatter in the universe. According to the Big Bang theory, the birth of the universe should have produced equal amounts of matter and antimatter. However, this would have led to their complete annihilation, leaving only radiation behind. Yet the observable universe is dominated by matter, suggesting that some unknown process tipped the balance in favor of matter. This asymmetry remains an unresolved puzzle that the Standard Model cannot address. Even the seemingly simple nature of neutrinos presents a challenge. Initially, neutrinos were thought to be massless, yet experimental evidence has shown they possess a tiny mass. This discovery has required significant revisions to the Standard Model, raising new questions about the origins of neutrino mass and its implications for particle physics and the broader universe. At its core, the Standard Model lacks a unifying principle that could explain why it contains the specific particles and forces that we observe. The search for a theory of everything, one that unifies all fundamental forces, including gravity, remains an ambitious and elusive goal. Such a theory would not only explain the particles themselves, but offer a more complete understanding of the universe's fundamental structure. Looking beyond the Standard Model, we encounter dark matter and dark energy, two of the most profound and enigmatic phenomena in modern cosmology. Despite being invisible and undetectable by traditional means, these entities make up about 95% of the total mass energy content of the universe. Dark matter constitutes approximately 27%, while dark energy accounts for around 68%. This leaves ordinary matter, everything visible and tangible, making up just a minuscule portion of the universe's total content. Dark matter is a form of matter that interacts gravitationally but does not emit, absorb, or reflect light. This makes it entirely invisible to the electromagnetic spectrum, complicating any efforts to detect it directly. The first hints of its existence came in the 1930s, when Swiss astronomer Fritz Zwicky observed that the motion of galaxies in clusters implied the presence of far more mass than could be accounted for by visible matter alone. Over the years, additional evidence, ranging from galaxy rotation curves to gravitational lensing and the cosmic microwave background radiation, has solidified the case for dark matter. Despite its invisibility, dark matter plays a crucial role in the structure of the universe. It acts as a cosmic framework, guiding the formation of galaxies and galaxy clusters. On the other hand, dark energy is an even more baffling force, responsible for the accelerating expansion of the universe. The discovery of dark energy in the late 1990s caught astronomers by surprise. Observations of distant supernovae revealed that the universe was not only expanding, but accelerating in its expansion, contrary to expectations based on gravitational forces. Dark energy is thought to be a property of space itself, evenly distributed across the cosmos. Unlike matter, dark energy does not dilute as space expands, and its exact nature remains an open question in physics. Its mysterious properties challenge our fundamental understanding of the universe, as it does not fit neatly into either the standard model or the framework of general relativity. These limitations and mysteries highlight that the standard model, while an extraordinary achievement in our understanding of the universe, is far from complete. It opens doors to new questions, new realms of inquiry, and ultimately, the possibility of revolutionary discoveries that could reshape our understanding of reality itself. As scientists continue their search for answers, the universe reveals itself to be far more complex and intriguing than we ever imagined. Dark matter, which comprises roughly 27% of the universe, is an invisible yet crucial player in the cosmic dance. It interacts with ordinary matter through gravity, but it neither emits nor reflects light, making it elusive to our direct detection methods. Instead, we infer its presence from the subtle gravitational effects it exerts on galaxies and galaxy clusters. These effects reveal themselves in the rotation rates and distributions of galaxies, where dark matter's invisible presence plays a pivotal role in shaping the universe's structure. Essentially, dark matter acts as a cosmic scaffold, providing the necessary gravitational foundation for galaxies to form and cluster together. The role of dark matter was particularly crucial in the early universe. In its infancy, the cosmos was a chaotic place filled with quantum fluctuations, tiny irregularities in the fabric of space-time. These fluctuations, though minute, were enough to influence the formation of the universe's large-scale structures, such as galaxies and clusters of galaxies. As dark matter's gravitational pull amplified these irregularities, it created potential wells into which ordinary matter could fall, condensing and cooling. This cooling led to star formation and the synthesis of heavier elements through nucleosynthesis in stars. Without dark matter's scaffolding, the universe as we know it may have failed to form the intricate web of galaxies that populate the cosmos today. On the other side of the cosmic spectrum is dark energy, which accounts for a staggering 68% of the universe's content. Unlike dark matter, dark energy does not clump together. Instead, it is uniformly spread across the expanse of space, exerting a repulsive force that accelerates the expansion of the universe. This mysterious force acts in direct opposition to gravity, pushing galaxies apart. The true nature of dark energy remains one of the most profound mysteries in modern physics. Its effects on the expansion rate of the universe are critical, influencing not only the future of cosmic structures, but also the formation of particles and the evolution of the universe itself. As the universe continues to expand, its density and temperature change over time, which in turn impacts the rate at which structures like galaxies and stars form. This acceleration of expansion influences the cooling of the universe, creating regions where particles can eventually come together to form atoms, molecules, and the stars and galaxies that make up the universe. Without dark energy, the universe would likely be contracting rather than expanding, and its evolution would look very different from what we observe today. Amid these cosmic forces lies the intriguing concept of supersymmetry, or SUSY, a theoretical framework that proposes a hidden symmetry between two fundamental categories of particles: bosons, which carry forces, and fermions, which make up matter. Supersymmetry posits that every boson in the standard model of particle physics has a corresponding fermion counterpart. Every fermion has a corresponding boson partner. These theoretical superpartners include names like squarks, for the superpartners of quarks, and selectrons for the superpartners of electrons. Supersymmetry has captured the imagination of physicists because of its potential to resolve some of the Standard Model's most perplexing issues, such as the hierarchy problem. The hierarchy problem centers on the stark difference in strength between gravity and the other fundamental forces. Gravity is vastly weaker than electromagnetism, the weak nuclear force, and the strong nuclear force. And understanding this disparity has long been a challenge. Supersymmetry suggests that new symmetries in the laws of physics could stabilize the mass of the Higgs boson, a particle that plays a key role in the Standard Model, but whose mass should theoretically fluctuate wildly according to quantum mechanics. Susie provides a natural explanation for why the Higgs boson's mass remains stable, offering insights into the weak scale and the overall structure of particle physics. Another tantalizing connection of supersymmetry lies in its potential to explain dark matter. As mentioned, dark matter constitutes around 27% of the universe's mass, but does not interact with light, making it invisible. Supersymmetric particles, particularly the lightest supersymmetric particle, LSP, could be the key to understanding dark matter. These particles are predicted to be stable, electrically neutral, and only weakly interacting, characteristics that would make them ideal candidates for the elusive substance that we observe only through its gravitational effects on galaxies and galaxy clusters. If SUSY particles exist, they could account for the unexplained gravitational forces attributed to dark matter. Despite the elegant theoretical promise of supersymmetry, experimental evidence remains elusive. Particle accelerators like the Large Hadron Collider, LHC, have been at the forefront of the search for supersymmetric particles. However, as of the latest findings, no direct detection of these particles has occurred. This absence of evidence has led to growing skepticism about the immediate viability of supersymmetric models, pushing the predicted masses of superpartners into higher ranges, beyond the reach of current experimental technology. Yet the search continues, as the potential discovery of supersymmetric particles would fundamentally reshape our understanding of both particle physics and cosmology. But does the Standard Model encompass all the particles that exist? Numerous theories propose the existence of particles beyond those currently described by the Standard Model. These theories arise from the need to address significant gaps, such as the nature of dark matter, the hierarchy problem, and the possible unification of the fundamental forces. Each of these theories builds on the successes and limitations of the Standard Model, offering potential new insights into the very fabric of reality. In this ongoing search for answers, the Standard Model, with all its elegance and precision, may only be the beginning. The journey to uncover the particles beyond this model is one that could lead to revolutionary discoveries. Particles that could unlock the mysteries of the universe, from the nature of dark matter to the origins of the cosmos itself. The quest for knowledge is far from over, and as our tools and understanding evolve, so too does the promise of new physics that could forever change our view of the universe. Among the most prominent of the theories that attempt to unlock the deepest mysteries of the universe are supersymmetry, SUSY, string theory, and various models involving extra dimensions. Supersymmetry, as we've seen, builds on the Standard Model by introducing superpartners for every fundamental particle, essentially doubling the known particle zoo. These hypothetical superpartners, although never observed directly, hold the promise of offering profound insights into some of the universe's biggest puzzles. SUSY could explain the nature of dark matter, as well as solve the hierarchy problem by stabilizing the mass of the elusive Higgs boson. Among the particles SUSY predicts are the gluino, the superpartner of the gluon, and the gravitino, which partners with the graviton, a particle that mediates gravity. While these superpartners remain theoretical, their existence would mark a groundbreaking shift in how we understand the cosmos. String theory, another powerful framework, proposes a radically different picture. Rather than envisioning elementary particles as point-like dots, string theory posits that these particles are actually minuscule, vibrating strings. The way these strings vibrate determines the properties of the particles they correspond to. In this model, the basic forces of nature, including gravity, are simply manifestations of the different ways these strings oscillate. String theory incorporates supersymmetry as a natural feature, predicting a vast array of new particles, including those responsible for gravity. By potentially unifying all fundamental forces in a single framework, string theory suggests that the key to understanding the universe lies not in discrete particles but in the very fabric of space-time itself. Furthermore, string theory hints at the existence of additional spatial dimensions beyond the familiar three. These dimensions, though too small to detect directly with current technology, could fundamentally reshape our understanding of the cosmos. Theories that explore the possibility of extra dimensions take this idea even further. In certain string theory models, as well as in the brain world scenario, the universe we experience could be just one of many dimensions. These additional spatial dimensions could be hidden from view, compactified to an extent that makes them undetectable by modern experiments. Yet, the implications are profound. Particles might move through these extra dimensions, which could offer an explanation for the relative weakness of gravity compared to the other fundamental forces. Moreover, this framework could also suggest the existence of particles associated with these hidden dimensions, opening up new avenues for research and understanding. One such idea comes from the concept of grand unification, which seeks to merge the electromagnetic, weak and strong nuclear forces into a single force using additional symmetry groups. The introduction of new particles, such as heavy-gauge bosons, could mediate transitions between different types of particles, like quarks and leptons, potentially reshaping the particle physics landscape. However, despite the elegance and promise of these theories, one of the major challenges they face is the lack of direct experimental evidence. Particle accelerators like the Large Hadron Collider are at the cutting edge of the search for new particles, and their discovery would not only provide confirmation for these theories, but also dramatically transform our understanding of the fundamental forces that govern the universe. The discovery of new particles, such as those predicted by SUSY or string theory, would be a scientific revolution, fundamentally altering our view of the universe's building blocks and how they interact. Gravity, though often overshadowed by the more familiar forces like electromagnetism and the strong and weak nuclear forces, plays a crucial role in shaping the universe at every scale. While its influence may be subtle in the realm of particle physics, gravity becomes significantly more important when we consider the broader cosmic picture. At the most basic level, gravity drives the formation of stars. As vast clouds of gas and dust collapse under their own gravitational pull, they create regions of immense pressure and temperature, allowing nuclear fusion to take place. This process, known as stellar nucleosynthesis, is responsible for the creation of the elements that make up everything around us, from the air we breathe to the stars that light up the night sky. Gravity's influence extends far beyond stars, however. It is also responsible for the formation of black holes, regions where gravity is so intense that not even light can escape. Near a black hole's event horizon, a region of spacetime where the escape velocity exceeds the speed of light, fascinating theoretical phenomena occur. For example, Hawking radiation predicts the generation of particle-antiparticle pairs from the vacuum of space itself. One of these particles falls into the black hole, while the other escapes, creating a fascinating link between gravity and quantum mechanics. This interplay hints at the potential for gravity to play a more active role in particle formation than we currently understand. On a grander scale, gravity shapes the very structure of the universe. The distribution of matter in the cosmos, from the delicate web-like structure of the cosmic web to the vast clusters of galaxies, is driven by gravitational attraction. This force dictates the movement of galaxies and the growth of larger cosmic structures, creating the intricate dance of celestial bodies that forms the universe as we know it. Gravity, though seemingly weak on small scales, plays a pivotal role in the larger cosmic structure, affecting everything from the formation of stars to the behavior of dark matter, the mysterious substance that makes up a significant portion of the universe's mass. In the vast expanse of the cosmos, a subtle yet powerful force underpins the very structure of the universe: gravity. This force, while overshadowed by the stronger electromagnetic and nuclear forces at the smallest scales, has a cumulative effect over vast cosmic distances and timescales that is fundamental to understanding the universe's evolution. Gravity governs how particles cluster together to form stars, planets, and galaxies. It's responsible for the formation of galaxies and the intricate cosmic web, weaving together the material that defines the universe. From the earliest moments after the Big Bang to the present day, gravity has shaped the universe, pulling together matter in the darkness of space and allowing the formation of the complex systems we observe today. This principle of gravitational attraction is not limited to small regions or brief moments. Rather, over immense timescales, gravity molds the large-scale structure of the cosmos. In fact, the formation of celestial bodies and galaxies themselves is a testament to the enduring power of this fundamental force. As the universe expanded and cooled, gravity's gentle yet persistent pull caused matter to coalesce, eventually leading to the creation of stars and galaxies. This process highlights the crucial role gravity has played in the ongoing evolution of the universe, guiding the dance of celestial bodies through space and time. As our understanding of the universe deepens, so does our recognition of how gravity interacts with the other forces that govern the cosmos. The theory of inflation, which emerged in the early 1980s, offers profound insights into the earliest moments of the universe's existence. Proposed by physicists like Alan Guth and André Linde, inflation suggests that the universe underwent an incredibly rapid, exponential expansion in the first fractions of a second after the Big Bang. This sudden and immense expansion stretched the universe by many orders of magnitude, far faster than the speed of light. Through this dramatic growth, the universe as we know it began to take form. The theory of inflation was developed to address key problems that were present in earlier models of the Big Bang, such as the horizon problem and the flatness problem. The horizon problem was one of the earliest puzzles for cosmologists. It asked how distant regions of the universe, now widely separated, could have arrived at the same temperature when light hasn't had time to travel between them. Inflation provided a solution by proposing that these regions were once much closer together. As the universe rapidly expanded, these regions were driven apart, but not before they had shared thermal energy coming into equilibrium. This resolution of the horizon problem was one of the first triumphs of inflationary theory, marking a significant shift in our understanding of the cosmos. The flatness problem was another challenge for cosmologists. Observations suggest that the universe is remarkably flat, meaning that the geometry of the universe adheres closely to Euclidean principles on large scales. If the universe had expanded steadily since the Big Bang, the initial conditions required to produce such a flat structure would need to be incredibly fine-tuned. Inflation, however, elegantly solves this problem by stretching the fabric of space so rapidly that any initial curvature was diluted, leaving behind a universe that appears flat to this day. In this way, inflation provided a solution to one of the most fundamental questions in cosmology. Moreover, inflation explains the origin of the large-scale structure of the universe. In the early moments after the Big Bang, the universe was a sea of tiny quantum fluctuations, each a minuscule deviation in energy and density. These fluctuations were stretched to astronomical scales by the rapid expansion of inflation. Over time, these fluctuations became the seeds for the growth of the universe's large-scale structure, with galaxies and galaxy clusters forming through gravitational attraction. This process continues today as the universe expands and evolves, revealing the ongoing influence of inflation. The evidence supporting inflation is compelling. Observations of the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang, have revealed subtle temperature variations that match the predictions of inflationary theory. The CMB shows that the universe was once in a much smaller uniform state, which was then stretched across the sky by inflation. The slight temperature fluctuations observed in the CMB are attributed to the quantum fluctuations that existed before inflation, amplified by the expansion to cosmic scales. These fluctuations eventually gave rise to the universe's structure, including galaxies, stars, and clusters of galaxies. However, despite its many successes, the theory of inflation also raises new questions. What triggered the inflationary expansion, and what caused it to end? These mysteries continue to challenge physicists, and various models of inflation have been proposed to answer these questions. Some models incorporate elements of quantum field theory and string theory, offering potential clues about the nature of the early universe and the forces at play during the inflationary period. Inflation not only sheds light on the universe's origins, but also addresses some of the most fundamental questions about its uniformity and structure. The cosmic microwave background, with its near-perfect uniformity, presents one of the most compelling pieces of evidence for inflation. Before inflation, regions of the universe that are now vastly separated were once in close contact, allowing them to reach thermal equilibrium. The rapid expansion then stretched these regions across the sky, preserving the uniformity we observe today. This uniformity of the CMB, however, posed a significant challenge before inflation theory. The horizon problem suggested that regions on opposite sides of the observable universe hadn't had enough time to exchange energy, yet the temperature across the sky was nearly the same. Inflation solves this by proposing that the observable universe expanded from a minuscule size to a vast one in a fraction of a second, allowing the universe to reach thermal equilibrium before being stretched. The small temperature variations that remain in the CMB are the result of quantum fluctuations, amplified by inflation and serving as the building blocks for the universe's structure. Through inflation, we gain a deeper understanding of the universe's origin, its uniformity, and the intricate processes that have shaped its structure. While there are still questions to be answered, the theory of inflation has undoubtedly revolutionized our understanding of the cosmos, offering insights into the forces that have governed the universe from its earliest moments to its vast present. The journey of discovery continues, and the full story of inflation remains an exciting frontier in cosmology. In the vast expanse of the universe, a mysterious puzzle remains, one that has fascinated scientists and philosophers alike for decades. Why does our universe seem to be made almost entirely of matter, with antimatter seemingly absent? The clues to this riddle lie in the fluctuations observed in the cosmic microwave background, CMB, a faint afterglow of the Big Bang. These fluctuations have been meticulously measured by groundbreaking experiments like the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite. Their results offer compelling evidence for the inflationary model of the early universe, where a rapid expansion occurred just fractions of a second after the Big Bang, shaping the cosmos as we know it. However, as we peer deeper into the heart of the universe, another equally perplexing mystery arises, one rooted in the very building blocks of matter itself, antimatter. Antimatter, in essence, is a mirror image of matter, but with opposite electric charge and other quantum properties. For every particle that constitutes matter, there exists a corresponding antiparticle that makes up antimatter. These antiparticles have the same mass as their matter counterparts, but carry opposite electric charges. Take, for example, the positron, the antiparticle of the electron, carrying a positive charge instead of a negative one, and the antiproton, which mirrors the proton in mass but carries a negative charge instead of a positive one. The concept of antimatter was first postulated by British physicist Paul Dirac in 1928, following his revolutionary work that extended quantum mechanics to incorporate the theory of special relativity. Dirac's equations predicted the existence of particles with the same mass as electrons, but with an opposite charge. In 1932, this prediction was confirmed when American physicist Carl Anderson discovered the positron, the first real evidence of antimatter, validating Dirac's groundbreaking theoretical work. The process of annihilation, when a particle of matter encounters its corresponding antiparticle, is one of the most remarkable phenomena in the universe. When this happens, the two particles annihilate each other, releasing a burst of energy, typically in the form of gamma rays. This annihilation demonstrates the powerful connection between mass and energy, as described by Einstein's famous equation, E=mc². While this annihilation seems like a cosmic erasure, it is in fact a profound reminder of the delicate balance that governs the universe. But antimatter is more than just a theoretical curiosity. It has practical applications that shape the world today. In medicine, for example, antimatter plays a pivotal role in diagnostic imaging, specifically through positron emission tomography, PET scans. These scans rely on the detection of gamma rays produced by positron annihilation to create detailed images of the human body, helping doctors diagnose and monitor conditions like cancer and heart disease. Furthermore, the study of antimatter holds immense significance in understanding the universe's origins. Cosmologists seek to answer profound questions about the Big Bang and why, despite predictions of equal amounts of matter and antimatter, the observable universe appears to be overwhelmingly composed of matter. The study of antimatter also pushes the boundaries of modern physics. Scientists are engaged in experiments to trap and study antimatter particles in laboratory conditions, a feat that has proven to be incredibly challenging. One of the most intriguing experiments involves antihydrogen atoms formed by combining positrons and antiprotons. Researchers are comparing the properties of hydrogen and antihydrogen to test fundamental symmetries of nature. These investigations could potentially reveal new physics beyond the standard model, offering insights into forces and particles that we have yet to fully understand. Now, let's turn our attention to CP violation, a phenomenon that plays a crucial role in explaining the asymmetry between matter and antimatter in the universe. CP violation refers to the breaking of the combined symmetry of charge conjugation, C, and parity inversion, P. In simpler terms, it means that certain processes where particles transform into their corresponding antiparticles behave differently when charges and spatial orientations are reversed. In the early universe, matter and antimatter were produced in nearly equal quantities. If CP symmetry had been perfectly conserved, the matter and antimatter would have annihilated each other, leaving behind a universe devoid of any matter. Yet, this is clearly not the case. There is a detectable surplus of matter in the universe, suggesting that CP violation must have played a role in tipping the scales toward matter's dominance. The observation of CP violation in certain elementary particle decays, such as those involving neutral kaons and B mesons, has provided crucial evidence that the laws of physics are not entirely symmetrical when it comes to matter and antimatter. These rare decays have revealed subtle differences between the behavior of particles and antiparticles, offering a potential explanation for the matter-antimatter imbalance that exists in the universe today. This discovery has opened up new avenues for research in particle physics, as scientists continue to explore the mechanisms that could have led to the creation of the universe we see around us. The investigation of antimatter and CP violation is not merely an academic pursuit, but a key to unlocking the mysteries of the cosmos. Every experiment, every discovery brings us one step closer to understanding the fundamental forces and particles that shape our universe. In the quest for knowledge, antimatter remains one of the most exciting frontiers in modern science, a frontier that, when fully explored, may reveal secrets that challenge everything we thought we knew about the universe. However, the exact origin of CP violation and its connection to the observed matter-antimatter asymmetry remain active areas of research in particle physics. But even as we push forward in this investigation, there are deeper questions that stretch beyond the confines of laboratories and equations, reaching into the very nature of reality itself. Can we ever truly understand the origin of the universe? This question has intrigued not just scientists, but philosophers and theologians as well, for centuries. It touches on the essence of human curiosity, our desire to know our place in the cosmos. As we probe the mysteries of cosmology and particle physics, we uncover more about the cosmic drama that began billions of years ago. Yet, despite our best efforts, there remains a veil of mystery shrouding the ultimate genesis of the universe. Theories like the Big Bang provide a solid framework for understanding how the universe evolved, tracing its journey from the earliest moments after creation. But when we peer into the very instant of the universe's birth, we encounter a realm where the laws of physics break down and our conventional understanding falters. This is a space where temperatures, densities, and energies exceed anything we can truly comprehend, a place where even the very fabric of space-time undergoes profound transformations. In these extreme conditions, the universe emerges from a singularity, an infinitely small, infinitely dense point. And yet, even as we strive to comprehend the origin of all things, we confront the limits of human cognition and the boundaries of scientific inquiry. Can our finite minds, relying solely on empirical methods, hope to uncover the deepest truths of existence? Or are there realms of knowledge that remain forever beyond our grasp, unreachable by human understanding? Some argue that the pursuit of knowledge is an innate part of being human, driving us to explore, to question, and to seek answers to the mysteries of existence. We are, after all, creatures who thrive on inquiry. Others, however, suggest that there are limits to what we can know, and that some aspects of reality may always lie just outside our reach. Could there truly be truths that remain forever veiled, or will we someday glimpse the full scope of the cosmos and our place within it? The concept of nothing also challenges our most fundamental assumptions about reality. How can we truly understand nothing? In modern physics, nothing isn't just the absence of matter or energy, it's a dynamic and complex entity in its own right. In the world of quantum mechanics, the vacuum of space isn't empty, it's alive with activity. Virtual particles pop in and out of existence, borrowing energy from the vacuum for brief moments before annihilating one another. This phenomenon, called vacuum fluctuations, suggests that even in what seems like emptiness, the very fabric of spacetime is constantly buzzing with unseen forces. Moreover, the concept of nothing is linked to some of the most profound mysteries about the universe's origin. According to the Big Bang theory, the universe began from a singularity, a point of infinite density and temperature. But what existed before this? Was there truly nothing before the Big Bang? Or are there realms of existence that defy our current understanding? These are questions that push the boundaries of science and philosophy alike, raising more questions than answers. But the study of particle physics doesn't just deepen our understanding of the universe, it also has real-world implications. Far from being a purely academic pursuit, research in particle physics has led to breakthroughs that have transformed the world we live in. One of the most notable applications of this research is in the field of medicine. Medical imaging technologies like positron emission tomography, and MRI, magnetic resonance imaging, owe their development to particle physics. These tools have revolutionized how we diagnose and treat illnesses, improving healthcare outcomes for millions of people around the world. In addition, particle physics has contributed to the development of advanced cancer therapies. Proton therapy, for example, uses beams of protons to precisely target tumors while minimizing damage to surrounding healthy tissues. This innovation, derived from particle physics research, has offered a more effective and less invasive option for cancer patients, providing new hope for many. The impact of particle physics extends beyond medicine, too. The World Wide Web, born out of the need to share data among researchers at CERN, has reshaped how we communicate and access information globally. Particle physics research has also led to advances in materials science, helping to develop new, more efficient materials for a variety of industries. Additionally, the creation of more sensitive particle detectors has enabled better security screening by environmental monitoring and even archaeological exploration. In the grand scheme of things, the seemingly esoteric world of particle physics has proven to be a profound catalyst for practical advancements that affect our daily lives. As we continue to explore the fundamental nature of the universe, who knows what other innovations await us? What once seemed like pure theoretical research now shapes the world in ways we never imagined. In the vast, uncharted realms of particle physics, the pursuit of knowledge is not merely an academic endeavor. It is the spark that ignites progress across diverse scientific disciplines. This quest, driven by the curiosity and innovation of physicists, engineers, and mathematicians, fosters collaboration that stretches beyond the confines of individual fields. These collaborations lead to groundbreaking advancements that ripple across various industries, inspiring change that could eventually touch every corner of our lives. As we peer into the future, the potential of particle physics to revolutionize our world is nothing short of astonishing. Though the breakthroughs may seem distant, their ripple effects are bound to shape the fabric of society in ways we can scarcely imagine. Among the most transformative possibilities are advancements in energy production and storage. If breakthroughs in particle physics, particularly in fusion energy, bear fruit, we could unlock a virtually limitless, clean, and sustainable source of power. Inspired by the plasma physics studied in particle accelerators, these innovations could dramatically alter our approach to climate change, energy security, and the very nature of how we power our modern civilization. Furthermore, the impact of particle physics extends far beyond energy. The field is on the precipice of propelling us into a new era of technology and computing. Quantum computing, which draws directly from the principles of quantum mechanics explored in particle physics, promises to radically transform how we solve the world's most complex problems. Imagine computers capable of processing information exponentially faster than today's technology, unlocking advances in cryptography, drug discovery, artificial intelligence, and much more. The potential for scientific innovation is immense, and quantum computing could be the key to unlocking solutions we've only dreamed of. But as we journey toward these extraordinary advancements, we must not overlook the ethical complexities that accompany them. The very scale of particle physics experiments, requiring enormous financial investments and cutting-edge technology, raises important questions about how resources should be allocated. Should we prioritize this type of fundamental research, or should these resources be directed toward immediate societal issues like poverty, healthcare, and education? While critics argue for redirecting funds, proponents maintain that breakthroughs in fundamental science often yield unanticipated solutions with far-reaching societal benefits. The history of science has shown that seemingly abstract research can result in transformative technologies that improve our lives in unexpected ways. Another crucial ethical challenge lies in the safety of these experiments. High-energy particle accelerators, while incredibly unlikely to cause catastrophic events, still pose potential risks, such as the creation of micro-black holes or the release of harmful radiation. Regulatory bodies and scientists must work hand in hand to ensure these risks are minimized and that public safety is maintained. However, safety is not the only concern. The very nature of the knowledge we uncover through particle physics also presents profound ethical questions. The discoveries made in this field could have wide-ranging implications for technology, medicine, and even weaponry. The potential to misuse these scientific advancements demands careful consideration, ensuring that the knowledge is not weaponized or exploited for harm. Equally important is the ethical framework surrounding international collaboration in particle physics research. The global nature of the field fosters cooperative efforts across borders, but this collaboration can sometimes raise issues regarding intellectual property, data sharing, and equitable access to resources. As nations with varying levels of technological development contribute to this body of knowledge, we must ensure that all participants have equal opportunities to contribute and benefit from the research. Transparent, fair, and open collaboration is essential to uphold the principles of scientific integrity and global progress. In the end, the promise of particle physics is undeniable, but so too are the ethical considerations it brings. As we continue to explore the fundamental nature of the universe, we must remain vigilant and thoughtful, carefully navigating the moral complexities that arise. By engaging in open dialogue and thoughtful reflection, scientists, policymakers, and society as a whole can ensure that the potential benefits of particle physics are realized in a way that aligns with our collective values and long-term goals. As we conclude this journey into the emergence of particles from the void, we are faced with profound philosophical questions that transcend the realm of science. Could the particles we study arise not from nothingness, but from the infinite potential that permeates the universe? This mystery invites us to ponder not just the mechanics of the cosmos, but also our place within it. The exploration of particle physics challenges us to expand our minds beyond traditional boundaries, embracing the vast, boundless possibilities that lie at the very heart of existence. How do you think particles came to life? How did it all begin? Share your thoughts in the comments below, and don't forget to subscribe to our channel Starflux. Thanks for watching.